If you're in the chat, just say hello. We'll be live in just a few minutes. Good morning, everyone. Happy Wednesday. So today we're going to cover the last chapter, our carboxylic acids. And so that will wrap up lecture. So kind of our plan. So wrap up, and that will be with chapter 17. So next week will be review. So again, if there's any topics you want me to cover, send me an email. I can record it. It'll be up live for you. Or just submit to me questions. I'll be taking questions live. So either way there. And so the week after that, that's essentially week 10. And then, of course, week 11, we will have our final open. And I think my other plan as well is this will be the last lab today. And I was kind of hesitant about that, but I know it takes me a while to get the data up for students that are doing it online, and I've been kind of reworking these labs. And actually this lab will be a little bit of an experiment. But that being said, it does take me a while to get the data up. I understand that for you, so I don't want to push the deadlines too much. So this will be our last lab. And I think the lab that I was planning to do for our final week is going to be an amine lab anyways. And that would be better pushed off to Chem 106. So our last lab today will be esterification. And that should be a lot of fun. And hopefully we'll get to play with the GC. And so we'll learn what that is. Great technique for separation or identification of compounds. Any questions or anything about last week of class or last lab? So let's look at carboxylic acids then and esters. So this is a general carboxylic acid group, and they are considered acidic because of this proton here. So this proton can be deprotonated, and so now we have our carboxylic anion now. And what makes these carboxylic acids, again, favorable. Okay, so let's draw outer structure. So let's just take a base. It could even be, water as our base. Has electrons on here. So it comes, deprotonates those electrons, then go to oxygen. So we have this structure. And then we can take these electrons, right, form a double bond that forces this charge onto here. And so now we have this delocalized negative charge. And so that works to stabilize it. So that's favorable. So this is an ester. So an ester is similar to carboxylic acid, but instead of having a terminal hydrogen, it has another group here. Then amides are also related, so they can have similar reactivity. And again, nitrogen can have this lone pair that can go. And so these are amides. And then so cyclic carboxylic acids are called lactones here. And so let's look at a couple of things. So actually let's skip to naming carboxylic acids. And then we'll come back to those lactones. But for naming carboxylic acids, the -ene ending is removed. And replaced with anoic acid. But what you will kind of start to learn is there's a lot of common names as well. And then we can also have special designations for the carbons. Oh, I don't like the way I drew that. I apologize. And so we can also designate the positions here. So this is going to be alpha, beta, gamma, delta, eta. It keeps going on. So now we can name our lactones here. So looking at this one, so this is our alpha position, right? It's our first position. So this would be next to our carbon of our carboxylic acid. So there it is, 1. So this is alpha. So the name for this compound is going to be alpha and then acyl acetone. Alpha acetyl acetone. And then so this one, now we have 2. So now it's alpha beta. So this compound is going to be beta, and now propio for 3. So propio acetone. And so this next one, now we have gamma because we're 3 carbons away. So gamma, 4 carbons total. So butyl, butyl actone. And then the last one in this example is going to be delta actone. So now let's look at other naming. So starting with the simplest one. So the formula is going to be HCO2H. So that only has 1 carbon. So that would look like that. And so the common name for this is going to be formic acid. So this is usually what you'll see in the naming. But then looking at our group, so we have methane, right? That's our base for meth. And so now we have meth, and the E is removed and replaced with enoic acid. So methanoic acid would be the IUPAC name. And so now looking at the next one, so this would be acetic acid. So now we've added a carbon. So again, the common name is acetic acid. So this is going to be your vinegar. And then its name. So we have F for 2. So ethanoic acid. So let's just pick another one. So 1, 2, 3, 4, 5, 6, 7. That's good. So 7 is actually ananthic acid, which I wouldn't know what this is without looking it up, but I would know what its IUPAC name is. So hep for 7, 1, 2, 3, 4, 5, 6, 7. Heptanoic acid. So let's look at some other examples. So now, what happens if we have a carboxylic acid in a ring? And so if we have a ring, then we can just add the suffix carboxylic acid. So in this case, we know how to name it. So 1, 2, 3, 4, 5. So cyclopentane carboxylic acid. Let's look at another one. This is a good one. So pay attention to the stereochemistry. So what would the name of that one be? So this one, so notice these wedges are on the same side. So this is going to be cis. And then, so this takes the 1 position. And now this can be 2, 3, 4, 5, 6. So cis 2-bromo cyclohexane, since it's 6. So cis 2-bromo cyclohexane carboxylic acid. So let's go back to another naming scenario that comes up. And so we mentioned that these carboxylic acids have a tendency to be deprotonated, and this means that we can form the salt, and so sometimes they're found as our salt and counter ion form. So let's look at how that changes it. So this would be naming salts of carboxylic acid. And so you can write cation plus acid name with ic change to 8. And so what does that mean? Let's go through an example. So we have this compound here. And so we can start off by naming just our sodium, just like we would any other compound, right? Sodium chloride, sodium bromide, etc. So we always start with a cation. So sodium. And then we need to figure out what acid it came from. So there's 2. So remember that was ethanoic acid. And so now we're just changing the ic to 8. So sodium ethanoate. And that would be our salt. The other name that you see for it, so if we go scroll back up. So if you remember, this was also known as acetic acid. That was its common name. So you may also see it written as sodium acetate. And usually this is what you see, just its common name. So let's do one other example. So we have this compound. Take a minute just to look at it. So we'll start with our cation. So this time it's potassium. And then we have 1, 2, 3. So propanoic acid. And I can't spell, so propanoic acid. So for me, I might have to write the acid first, just so I can see it. And then drop the ending, so I know that I need that O in there. So propanoate would be our salt. And, I try not to be too harsh with spelling. Again, I can't spell, but for these, take the time because you have propanoic acid and it says to just drop the ick. So I don't want you dropping that O. That's my emphasis, that the O is kind of important here because that really indicates that it's a salt. All right, let's look at some extra practice. I didn't know this naming carboxylic acids would go so long. I was going to put esters on the same page. So let's start this one. So what would the name of this one be? So let's count our carbons. So 1, 2, 3, 4, 5 for our length there. And so our hydroxy group is in the 3 position there. So we can go 3 hydroxy, and then it was pentane or pentanoic since we're doing an acid. So pentanoic acid. So let's try a different one. This is kind of interesting. So let me draw out the structure and then we'll look at it together. And so now, not only do we have, so this is, right, our carboxylic acid, but now we also have an aldehyde group here. And so it takes the interesting name of oxo. So carboxylic acid plus ketone or aldehyde. The CO becomes oxo. And so now let's break this down. So first we need to count our carbons. So 1, 2, 3, 4. So that puts that oxo at that 4 position. So now we would say 4 oxo and then 4 carbons, so butane or butanoic acid. You can see I almost lost that O there, but and so just to practice. So pretty similar. So what would the name of this one be? Of course, this takes priority 1. So 1, 2, 3, 4. So 2. Oxo. Still 4. So butanoic acid. So do we feel good about that one? Any questions? So now let's look at esters. And I feel like they're pretty similar. We covered ether groups. So you could kind of assign, assign either one, and kind of name both sides. And so let's look at esters because they're pretty similar. So let's look at this one. So let's break it down. So we have our esters are named as the alkyl chain from the alcohol group is a substituent. So this is from our alcohol side. And we'll be doing this in class. So this is from methanol. And so this can be named as methyl then. We don't need to assign a number. And the name of the parent chain with the carboxylic acid. And so this is ethanoate. So methyl ethanoate. So then another example. So what would the name of this one be? So we have our alcohol group. So ethyl. 1, 2, 3. So propanoate. And so we'll be forming esters in lab today. And so let's look at a couple of other examples. And so now the chloro is on our alcohol part. So we need to name it. So this will be 1 for the alcohol. So 1 chloro methyl. And then this is 2, so ethanoate. And so compare that to similar. So now this would be methyl, because now we just have a methyl on this side. And now this would be 2-chloro, since that's 1, so that's 2. So 2-chloro ethanoate. And let's kind of do the opposite now. So if we have octyl ethanoate, what would that be? Give everyone a minute or so. So octyl, that would be on our alcohol side. So now 1, 2, 3, 4, 5, 6, 7, 8. So octyl and then ethanoate. So 1, 2. So any questions about those? So now let's look at some reactions. And so again, this is what we're going to be doing in lab today. So we're going to be starting, and this is why it'll be nice to go through the mechanism. And so if you look, we're starting with the carboxylic acid. We're adding the acid, so we're going to be losing the OH here from our carboxylic acid and forming water. So it's going to lose this, form water, and then we'll make our ester with whatever our group is on with the alcohol. And so let's start off with our reaction. So now we have 1, 2, 3, 4. So this is butanoic acid plus methanol in the presence of an acid catalyst, in this case sulfuric acid. And so again, we would lose that, so keep our butane. Add the alcohol, so O, H there, or CH3, I don't know why I said H. So now let's look at the mechanism. So I'm going to rewrite. And so the first step is we're in acidic conditions. So I'm just going to, for shorthand, write H plus here. And the first step, so I'm going to try to show my mechanism in red. So again, we have these lone pairs on oxygen. So they're going to be protonated. Can't seem to tell the difference. So still double bonded. Now it has a formal plus charge there. So the next step, we have our nucleophilic carbon here. Or excuse me, nucleophilic reaction. So our alcohol is going to come. So methanol. So this is our nucleophile. This wants electrons. So this will attack here. And so that causes those electrons to go back up to oxygen. So that will be happy. And so let's just draw our current intermediate. Oops. That's not correct. So we move those electrons up. I apologize. So now that's fine. Now we have our OH there. So methanol. And then formal charges. So this has a positive formal charge. You can draw in our electrons there. And draw in our electrons. And so the next step is a proton transfer. So our proton from here is going to move over to here so we can have water as a leaving group. So let's kind of write that. And so there's different ways. And honestly, I've seen professors get annoyed with proton transfer mechanisms. So you might want to say deprotonated, protonated. It kind of depends on your professor, actually. So I'm okay with proton transfer. They're also kind of close. So it's good. Grab that there. And so PT, again, stands for proton transfer. And so now let's redraw our structure. And so this, that was formerly the OH on our carboxylic acid. Now it has another proton. This is fine. So now it's just alcohol group there. And I should have drawn this to show our lone pairs. And so water can leave as our carbonyl reforms. And so now draw that. So this still needs to get deprotonated. Oops. Sorry. 2, 3, 4. 1, 2, 3, 4. Always count your carbons. I can't emphasize that enough here. And so last step. Now we just need to get deprotonated. So our base, or since we have all our sulfuric acid catalyst, this can come, deprotonate, and that leaves us with our product plus our catalyst. So any questions about that? And so similarly, you can do the same reaction with an amine. So this is called a Fischer esterification. You could also call it a condensation reaction since you're forming water here. And actually, if you set up your reaction properly with what's called a Dean Stark, let me pull up a picture. And so this is a special apparatus here. Oh my goodness, every picture I pull up. So this is a Dean Stark apparatus, specifically this part right here. And so what you would do, you would have your reaction refluxing or boiling. And so if it's boiling, or in chemical terms we say refluxing, that means that it's evaporating, going up, and then you have this condenser on here. So that condenser has water on the outside jacket, your solvent's on the inside, and so it's much cooler here, so your solvent goes back down. And if you have water, though, water has a density that's lower, or excuse me, greater. I meant to say it's the lower layer. So it is greater, so therefore it's the lower layer. And so this would work for ether, for example. Ether is less dense, or hexane. It wouldn't work for DCM. DCM is actually heavier than water, or more dense, excuse me. And so what happens is you have this little offshoot here. So of course, all your solvent will start gathering here. But as it continues, your organic solvent should be on the top, because again, you're going to pick an organic solvent that is less dense than water. And so eventually that will funnel back in, and you'll collect your water over here. And it's cool because you'll see that water layer forming. And if it gets really full, some of them even have this little stopcock so you could drain it through. I've never, well, yeah, I haven't ever either had a need for that, let's just say. So usually there's, not that much water. Maybe you'll collect it halfway full. The rest will be your organic, and it'll keep going in. But this is a great way to drive your reaction forward. Because if you're thinking about chemical equilibrium, if you're removing one of the products, aka water, that will continue to help drive your reaction. And I get excited too when we get to talk about real life lab applications. And so again, similarly, we have a similar mechanism, so we'll lose that OH. And then, just like our alcohol will want to attack here, our amine can do the same thing with that nitrogen. So that nitrogen can attack here, so we would essentially have the same mechanism. And then kind of going now in the reverse. So we said that these were condensation reactions. And so the opposite of this, if you're losing water, would then be reacting with water. And so in this process, now we start with an amide. Notice that that's what we formed from our amine plus our carboxylic acid. We formed an amide. But then we could take this amide, react it in the presence of acid and heat, and form our carboxylic acid and our amine. And so notice, right, that's kind of opposite from what we did. And so let's look at this mechanism since it's a little different. Nope, sorry. Made space and then I lost my space. And so I'll just start with our amide. Again, just a simple amide. And we're in acid. You know, sometimes I'm conflicted as to what to write. I just want to emphasize this, that H plus doesn't exist. It equals hydronium. But sometimes chemists are lazy, especially if you draw out a million mechanisms. You just want to draw H plus to signify any sort of proton source. So we can take this, it'll get protonated. So that's our first step. This is in equilibrium. So plus charge there. Now we need to add water. So this is a good place to attack. We've seen this before. Or now this place, right? So we have this carbon wants electrons. So water goes in for the attack here. So we'll attack here, moving those electrons up. Let's draw that. And now I'm just abbreviating NH2 there. So now this has our positive charge. And so now the next step is we're going to deprotonate this. So we'll say water comes along and plucks this off. So let's draw that. I don't know why black keeps disappearing. So OH. Now this is an OH2. We have our amine. Now the next step, we could protonate our nitrogen. So nitrogen has that lone pair. We have H plus, or water floating around. Now let's draw what we have. Ah. So now we have this protonated amine here, plus charge on that nitrogen. And so what's going to happen is you can reform your carboxylic or your carbon double bond here. So we'll reform this. This is our leaving group. So now this is going to leave. Now we have this species, so we'll have to deprotonate it. So there's our carboxylic acid reforming, and then our amine product. And so, again, last step, deprotonation. So this nitrogen can actually come along. Little drunken arrow here for some reason. There we go. Go back. So now we have made ammonium chloride as our counter ion. There is our product. Plus its counter ion. Any questions about that? I just wanted to point out these triacyl glycerols as well. And they're tri since you have 3 of them connected together. And let's see, other things of note. So when it comes to boiling points, just keep in mind, the same thing, you're looking for hydrogen bonds. And so some of your amines may have higher boiling points because they have more hydrogen bonds. Carboxylic acids, of course, should have high boiling points. And then, so the other thing is, right, these carboxylic acids are kind of everywhere. Acetic acid, again, is vinegar. Just looking at the book too for inspiration. Alpha hydroxy groups can be used in beauty products, so tartaric acid, salicylic acid, that comes up a lot. Aspirin and other inflammatory agents. Melatonin is an amide, and so lots of amines and amides are drugs. And again, all those esters are fragrance-y, so wintergreen, that's going to be methyl salicylate. Apricots is pentyl butanoate. Ethyl butanoate is mangoes. There's also like the banana ester smell. And soap. Soap is covered in here, even though I feel like we did soap other places. But soap works in that. So we have our kind of carboxylic acid counter anion here and a long chain. And so we have a hydrophilic end. So this charged polar side wants water. This is hydrophobic, this long chain. And so they can kind of orient themselves in. You have your non-polar interior and your polar exterior. And so this works to have cleaning power. So these, again, hydrophobic parts are good for grease. And so that cuts through your grease. And then again, it's attached to this hydrophilic part though that works away to help interact with the soap. And so the other last topic is just polymers. So there's a lot of polymers that are based off of these. So one of them being nylon. And this is actually a synthesis I would like to do. So you have one way is your adipic acid here, and then this hexylmethylamine diamine. And notice, right, we have a carboxylic acid on both ends, amines on both ends. And so that means you can chain them together in the reactions we just saw. So, right, we can lose this, attach our amine there. So you see that to make our amide groups here. But then on this one, right, it's going to react with another end. And so it can just keep going and going. And that's how we make pantyhose. And so Kevlar, actually, let's pull this up. Kevlar is pretty cool. So Kevlar was invented by DuPont, by this chemist, so Stephanie Kolek. And I think it was actually an accident or something. So she was working for DuPont, trying to look for extreme fibers. And so she accidentally somehow made these ordered crystalline fibers. And then ended up being Kevlar. So it's super strong fibers. It's really fascinating. And of course, they've gone to use Kevlar in all sorts of projects. And so, kind of the issue, or maybe not issue, but double-sided sword with that is, so we make these great polymers and they're bonded, they have really strong chains and all this, but kind of the flip side of that is they're hard to degrade and they can kind of stick around in the environment like plastics. And so this is just kind of encouraging you to recycle and recycle by numbers if you can. So PET, that's kind of the easiest to recycle. And then it goes on from there with the numbers. So excuse me, let's go ahead and stop there for today. We covered a lot in terms of naming and mechanism. So I would look at this naming, and all you really need to know is the reactions, but it's always good to look at these mechanisms and kind of appreciate them and understand them. And then hopefully some of these little fundamentals kind of come back and remind you, especially if you're going on to more chemistry or want to take OChem or are preparing for MCATs or med school or anything like that. Well, thank y'all. And thank y'all for a great quarter. We're almost to the end. And so again, next week will be more review. So send me your questions. I look forward to hearing from y'all. Have a great day. And then I'll see some of y'all in lab today. So we will do that. Thank you.